So just to review a little bit, the last couple of weeks we've been talking about the discovery cycle and the credibility cycle, as Grinnell describes them. And the worry here that we've been kind of working with was that honest, serious, intelligent researchers might be biased in various ways. And the question for us was, how does the scientific method deal with those honest biases? The people just trying their best to do good science, but nonetheless not being able to because of the way our brains are wired, essentially. And the hope for scientific credibility, the idea that science would come up with reliable, intersubjectively valid ideas, was in the credibility cycle. That is, in the community, those biases would hopefully be identified or canceled out somehow. Okay, so all of this was assuming that the people involved are honest, serious, diligent people. And I think by and large, that's going to be a good assumption about the scientific community. I mean, people don't get into science because they're thinking they're going to get rich and famous. It's just not the best way to do that. So almost everybody in scientific communities really wants to contribute to the project. However, we do have to discuss the possibility, and in fact the actuality, that not all scientists are behaving well all the time. So we live in a pretty messy world, and there are some pretty difficult incentive structures in the process of science as we know it today, which leads people to not follow the rules all the time. So this week I'm going to look a little bit at the question of scientific integrity and what happens when scientists are less than fully honest or less than fully forthcoming. And the question is, how does the scientific method, as it's practiced today, deal with that question? So recall from our previous discussions that getting credit for a discovery claim is central to the life of a scientist for at least a couple of reasons. I mean, one of which is that's probably why they got into science in the first place. They want to contribute to the sum of human knowledge, which is this beautiful, noble goal. And right there beside that motivation is the fact that if you don't get credit for discovery claims, you don't get grants and you don't get good jobs so that you can continue to be a scientist. So having publications, this is a little image of somebody's sort of record of not just what they've published, but how many times what they've published has been cited. And that's the real metric for what's likely to get you grants, what's likely to get you good, secure, like scientific jobs. So we've got this incredibly noble, high-minded motivation of contributing to the sum of human knowledge, and also the fact that if you don't get credit for discovery claims, you don't get to be a scientist anymore. So those two running in parallel can make people do some unfortunate things. So when we're talking about scientific credibility or scientific integrity, I think we should be careful to distinguish at least three different things, even though maybe the lines between them will be a bit blurry. So let's distinguish making choices in how you run an experiment and how you analyze the data from maybe being biased about the results. We talked about bias last time, and straight up fraud, like lying and cheating. Okay, so I'm going to argue that there's maybe not a very crisp line that we can draw between making choices and maybe being biased. Actual fraud maybe is a little clearer, but in this video, we're going to talk about the kind of choices that scientists make and how they can shade into creating a biased picture of the data that you're working with. Okay, so scientific choices. Okay, so in any kind of real world project, there are always choices to be made about how you're going to run the experiment and how you're going to analyze the data. So the kind of choices you're going to make about how to run the experiment are going to vary widely from discipline to discipline. In this video, I'm just going to talk a little bit about how to analyze the data that you've got, because that's slightly more universal, slightly more widely applicable. But like, if you can see this image, they've made a choice about where to draw the line of best fit. So you've got a bunch of data points, you want to draw a line through it that is to generalize from the individuals to what the overall trend is. And they've drawn a straight line. And if you're looking at the image, you might think that they could have made a better choice there. But there really is no preset universal set of rules for how to make choices like drawing line of best fit. your paradigm will have some guidance, but there's not clear, hard, and fast rules. So judgment calls are necessary. The point here is just that in every scientific project at the level of modern complexity that we're at, you need to make choices, and those choices are generally going, or very often going to be, judgment calls. Okay, so let's talk a little bit about p-values and the ways in which judgment calls have sort of affected this and play into this sort of area between scientific choices and maybe bias or fraud. Okay, so p-values, one of the most famous or maybe infamous measures of statistical significance. So this is very roughly, and I'm probably going to, for the stats wizards out there, I'm probably going to get this slightly wrong, but to get the intuitive idea, a p-value is roughly a measurement of how likely a given correlation is to be just chance. So you've got two variables, and your question is, are these variables correlated? So if you increase one, does the other increase, or whatever? And your null hypothesis is that they're just unrelated. So the color of socks that I wear is unrelated to the motions of Venus. So my null hypothesis is those have nothing to do with each other. But if I collected a bunch of data about those two variables, once in a while there would appear to be a correlation. And a p-value can tell you how likely, so the measuring the p-value is how likely is that correlation to be just a coincidence rather than evidence of a real causal connection between two variables. So very small p-value means it's really, really unlikely that two things happen to be correlated. So imagine every time I wore blue socks, Venus did a specific thing in the sky, and that happened again and again and again and again. You'd start to think, oh, maybe there is something here. A large p-value means that it's quite likely to be chance. So if I only ever wear blue socks and Venus keeps doing its thing, well, those correlations are probably just chancy, right? Okay. So there's a kind of magic value for p-values that the scientific community, many different disciplines have sort of converged on. The standard cutoff for what we call statistical significance is less than 0.05. So that's roughly equivalent to saying something is statistically significant. An apparent correlation is statistically significant if there's less than a 1 in 20 chance that it's just a coincidence. So that's a kind of, it's a reasonably nice point to choose. I mean, there's nothing wrong with less than 0.05 as a cutoff for statistical significance. You might ask why 0.05 is the standard cutoff, and the answer is kind of no reason. Not no reason at all. Actually, it's if you look back into the history of this thing, people have been using something like p-values for a couple of centuries. The way it's formalized today traces back to the early 20th century, and a lot of credit goes to, for the specific way it goes to a statistician called Ronald Fisher in the 1920s. And if you go to the texts where he's explaining how he came up with 0.05, he says things like that it's conveniently similar to other statistical measures that he's using, and it being conveniently similar is helpful because he's in the 1920s. It's pen and paper, right? Like they're using maybe a mechanical calculator, but they're not doing these calculations with computers. So little shortcuts like that are very helpful. In this case, it was p less than 0.05 is pretty close to being off by 2 standard deviations, if you're familiar. So he picked a number kind of out of a hat, kind of out of calculation convenience, and that number was less than 0.05, so a 1 out of 20 chance that the thing is just a coincidence. Okay, so that's one of our measures for statistical significance, and getting a p-value of less than 0.05. So being able to reject the null hypothesis, being able to say that there is a real signal in your data with that it's less than 0.05 statistical significance, has become a kind of almost universal cutoff for being publishable. So hitting this mark qualifies you in some sense to be published. Now, here's something odd that's could have grown up around this. So this was kind of an arbitrary choice. We're talking about choices in scientific methodology. Fisher's choice of less than 0.05 was, while not completely arbitrary, it certainly wasn't motivated out of any kind of deep understanding of statistics or science or anything like that. It was just a kind of convenient cutoff point. He could have picked 1 out of 100 chance, or 1 out of 1,000, or 1 out of 10, right? And if you go back and look at Fisher, he says, there's nothing special about this number. We should pay attention to the whole range of p-values because those tell you different things. But modern scientific methodology has sort of settled in on less than 0.05 as an important cutoff. And now when you look at the literature for what's published, you see some very strange signals. So here's a paper on what's called p-hacking. P-hacking is manipulating the way that you either analyze or collect your data in order to get a p-value less than 0.05. Now, if we were just kind of doing statistical analyses with no intuition or understanding of what that cutoff was, you'd expect these p-values to be sort of randomly distributed, right? You'd get some number. But when people go through, so this is from a paper called P-Hacking in Clinical Trials from 2017, they took a randomly selected sample of 575 p-values from medical studies, and what they found was a very strange spike just under 0.05 for their p-values. So that's that big in the middle of this graph here. That's that big spike where there's a lot of studies getting just under 0.05 for their p-value. And again, if this was random, if it was just random, like if it was uninfluenced by anything, you'd kind of expect those p-values to be very nicely distributed, but there's a big spike here, which is evidence that something funny is going on. And that funny thing, not funny haha, but kind of funny sad, is something like p-hacking. Okay, so there's always a relevant xkcd. This is a webcomic if you've never seen this. Here's the best explanation I've seen on the internet of what one version of p-hacking is. Okay, so in this case, suppose that you're investigating whether jelly beans cause acne. Okay, so jelly beans cause acne, scientists investigate, and the scientists find there's no correlation. The number of so you're trying to see if there's a correlation between two variables, the number of jelly beans a person eats in a day and their level of acne. Okay, so they run a study, they find, there's no statistically significant correlation between eating jelly beans and having acne. Case closed. However, suppose somebody says, I hear that it's only a certain color that causes it. So what they do is they go back into their data and run 20 separate analyses. Okay, so there's no link between purple and acne. There's no link between brown jelly beans and acne. There's no link between, and so on and so on and so on, except for one single case, green jelly beans. Turns out green jelly beans showed a statistically significant correlation with acne. So what they've done is taken their overall data, where there was no statistically significant correlation, broken it up into 20 little subgroups, looked at each subgroup individually, and found in one of them, hey, look, a statistically significant correlation. But remember what a p-value tells you. It says that there's a 1 in 20 chance, or less than a 1 in 20 chance, that this is just a coincidence. So if you run that 20 times, the chances are actually pretty good that you're going to come up with a seemingly statistically significant signal between those two variables just by chance. And then it gets reported in Science News as green jelly beans are linked to acne with 95% confidence. So running multiple different analyses until you come up with one that happens to have an apparently statistically significant correlation between two variables is one form of p-hacking. And I hope you can see that this is a pretty serious subversion of what science is supposed to be doing. And this is the point at which, remember those science fair experiments that you did where they made you say your hypothesis ahead of time? This is a case where saying your hypothesis ahead of time actually does matter. because in the original case, they disconfirmed the jelly beans had anything to do with acne. But if you dig and dig and dig in the data, you can find something that looks like a statistically significant correlation. It's not the hypothesis you started from, but you can find one by p-hacking hard enough. There's a bunch of different ways of doing p-hacking. I'll just mention one other one very briefly. I mean, so we talked about distinguishing noise and data. And an extremely common thing to do in legitimate, serious, well-run scientific experiments is to exclude some of your data. You don't include every single data point because some of them are just weird and unexplained. So no experiment is perfect. Some of them are just going to go a bit funny. Like some of the trials are going to be odd. And so it makes perfect sense to exclude if you got one point that's just way out there and you don't know why, and it doesn't seem to be a signal or a sign of anything, you just kind of leave it out of your analysis. And this is the done thing. This is not something that I think is unreasonable to do. You want a clean picture of the signal that you're trying to understand. Excluding outliers makes perfect sense. But I'm not sure where the line is. So it's very hard to draw a principled line between excluding some outliers and scrubbing data points that get you just over the bar for not being statistically significant. You want to get that number just under 0.5. So maybe this one looks like an outlier and that one looks like an outlier. And very often these are judgment calls that scientists have to make. So there's not like a principled rule that they should be following to decide which are the outliers and which aren't. It differs by discipline and by discipline to discipline, and it's also often just a straight up judgment call. So when does it make sense to exclude outliers, and when is it sort of p-hacking? When is it massaging the data? It's hard to say. It's genuinely hard to say. Okay. So this video has been about this question of choices, biases, and fraud. What I just described to you was p-hacking, which is manipulating the data in subtle ways. But I want to insist that it's just not super clear where the line between cleaning up your data and manipulating it is. So there's a very fuzzy boundary between making very reasonable choices about how to collect and analyze your data and introducing a bias into that data that makes it such that you pass the fairly arbitrary line of less than 0.05 for statistical significance. So it's surely not fraud to do more than one type of data analysis. It's surely not fraud to collect a lot of data and not use it all. But there does seem to be some point at which this shades over into less than fully honest science. And it's really hard to draw the line there. Okay, so next video, I'm going to talk about this third element, like straight up fraud. So we'll talk about the actual clear lying and cheating version of this. Thanks.